The first question we're going to work on is question 11 from the 2021 Pascal competition. We're given an operation, the upside down triangle, where A upside down triangle B outputs A to the B times B to the A. So what we're asked is, what do we get when we have 2 upside down triangle 3? Basically what we can do is to treat the upside down triangle as a function. So basically where 2 and 3 are the inputs. So we have A equals 2 and B equals 3. The important thing to know is that the order A and B matters. So then if we have this, then we can just plug this into here. We have 2 to the 3 times 3 to the 2. And from here, 2 to the 3 is equal to 2 times 2 times 2. And the 3 to the 2 is equal to 3 times 3. And this is equal to 8. This is equal to 9. And we get 72. Now let's move on to the next question. This is question 25, the last question of the same Pascal competition. So we're given a list of integers, 1, 2, 3, all the way up to n minus 1, and then n. Then we're given 4 positive integers, p, q, r, s, such that 100 is less than p, is less than q, is less than r, is less than s. So what we're told is if we have the original n numbers and then we subtract these 4 integers, the remaining list has an average of 89.5625. Finally, we're asked, how many different possible values of s can there be? The first thing we would want to do in a question like this is to convert this into a fraction. And since this is a calculator exam, we can just start by guessing denominators. What we eventually work out is that this number is equal to 1,433 over 16. This will be very useful in the future. Since we don't know what PQRS is, and we only need to subtract all 4 of them, what we can do is to just express the sum of these integers, P plus Q plus R plus S, as a new integer. We can just call K. Next, what we want to do is find the way to express this list of integers minus these 4 integers as an average. So what we would do is find the sum of these integers and subtract the sum of these integers, which is k, and then divide by the number of numbers. This is very standard in finding averages. The average of the list is n times n plus 1 over 2, since these are just consecutive natural numbers. Next, we would subtract this, and since we know that's k, we can just write minus k. Finally, since there were originally n numbers in this list, if we subtract 4 numbers, then very clearly n minus 4 numbers. We know the average is 89.5625, which is the same as 1433 over 16, so we can just write that here. For the sake of conciseness, we can write this whole mess as another variable, just to make things look nicer and easier to understand. So we can define n plus 1 over 2 minus k equals a new integer equals s. This seems kind of arbitrary, but it just helps visualize things a bit. Next, what we can do is cross multiply. We have 16x equals 1433 times n minus 4. Since we know s and n are both integers, what we can do is to say that s must be a divisor of... Next, what we can do is cross multiply. Since we know s is a sum of numbers, this must be... Next, what we can do is cross multiply. We take 16 times x equals 1433 times n minus 4. Since s is a sum of integers, s must also be an integer, and n has to be an integer as well. What we can do then is to say that 1433 has to be a divisor of s, and 16 has to be a divisor of n minus 4. So the next step is to actually make an assumption. We can do this by seeing that PQRS is part of the list 1 to n. Since all of PQRS is greater than 100, that means n necessarily has to be greater than 100 as well. And since we have more than 100 integers and we're taking out only 4 integers, we don't expect the average to change by much. So then we can see that here, 89.5625 is really close to 90. So we can just make an assumption that the average of the original list is probably 90. From then, it's really clear to see that the original n probably was 180, and we can work on from there. Since we know that 16 is a divisor of n minus 4, or that n minus 4 is a multiple of 16, this can be kind of a sanity check for us to make sure that this estimate seems reasonable. If we take 4 away from this, we get n minus 4 equals 176. And putting this into our calculator, 176 divided by 16, we get that n minus 4 is indeed divisible by 16. So this checks out. So what we can do now is plug n minus 4 equals 176 back into this original equation. So what we get is that s over 176 equals 1433 over 16, and we can just solve for s, and using our calculator we see that this is 15,763. So then what we can do is to actually find what the original sum turns out to be. How we do that is to plug this n equals 180 into the original sum, n plus 1 over 2. So we just take 180 times 180 plus 1, or 181, and divide by 2. And from here, what we get is 16,290. Then what we can do is to take 16,290, which is the original sum, minus 15,763, which is the sum after we take away the 4 integers. What this gives us is the sum of the 4 integers, and if we actually carry out that, we get a final value of 527. So now we see that P plus Q plus R plus S equals 527. Now what we need to do is actually find what PQRS could be. So now what we need to do is to actually find what PQRS can actually be. So the constraints are given is the original constraint that PQR. So now what we have to do is actually find what could PQRS actually be. So the original constraint is 100 is less than P, less than Q, less than R, less than S. So from what we can see here is the minimum value for P is 101, and all these numbers must be distinct. But there's actually another constraint. Since we know that PQRS is part of the list from 1 to n, that means PQRS cannot exceed n. This also sets an upper bound on what these numbers can be. So then we see that PQRS has to be less than or equal to n. And we figured out from the last bit that n equals 180. So this sets an upper bound on all 4 of these numbers. So now what we have to do is find the minimum and maximum values of the 3 consecutive integers. To find the minimum value, we set the odd integer out as the largest possible value, which is 180. So then we see that the sum of the 3 consecutive integers, x, plus the odd integer out, 180, has to equal 527. Using basic arithmetic, we find that x equals 347. Since 347 is not divisible by 3, we need to find the number right above 347, which is divisible by 3, and that number happens to be 348. Dividing by 3, we see that we get the number 116. That means the middle number has to be 116. So the number right below has to be 115, and the number right above has to be 117. These are the minimum values for the 3 consecutive integers. This is probably 90, From then, it's really clear to see that the original n probably was 180, and we can work on from there. Since we know that 16 divides n minus 4, that means n minus 4 must be a multiple of 16. So since we guessed that n equals 180, then that means since we know that 16 is a divisor of n minus 4, or that n minus 4 is a multiple of 16, this can be kind of a sanity check for us to make sure that this estimate seems reasonable. If we take 4 away from this, we get n minus 4 equals 176. And putting this into our calculator, 176 divided by 16, we get that n minus 4 is indeed divisible by 16. So this checks out. So now, plugging back into this formula, we can figure out what the original average was. No. So now what we can do is plug n minus 4 into this equation. Now we get that s equals 1433 over 16 times n minus 4, which is also 176, and we can just work this out into our calculator, and eventually we get 1563. So what we can do now is plug n minus 4 equals 176 back into this original equation. So what we get is that s over 176 equals 1433 over 16, and we can just solve for s, and using our calculator we see that this is 15,763. Now we also want to find the original sum of the numbers of the list. So we can just plug n equals 180 into n plus 1 over 2. Then we get 16,290. So these two numbers will be important for later. So then what we can do is to actually find what the original sum turns out to be. How we do that is to plug this n equals 180 into the original sum, n plus 1 over 2. So we just take 180 times 180 plus 1, or 181, and divide by 2. And from here, what we get is 16,290. Then what we can do is to take 16,290, which is the original sum, minus 15,763, which is the sum after we take away the 4 integers. What this gives us is the sum of the 4 integers, and if we actually carry out that, we get a final value of 527. So now we see that P plus Q plus R plus S equals 527. And now what we need to do is actually find what PQRS could be. So now what we need to do is to actually find what PQRS can actually be. So the constraints are given is the original constraint that PQR. So now what we have to do is actually find what could PQRS actually be. So the original constraint is 100 is less than P, less than Q, less than R, less than S. So from what we can see here is the minimum value for P is 101, and all these numbers must be distinct. But there's actually another constraint. Since we know that PQRS is part of the list from 1 to n, that means PQRS cannot exceed n. This also sets an upper bound on what these numbers can be. So then we see that PQRS has to be less than or equal to n. And we figured out from the last bit that n equals 180. So this sets an upper bound on all 4 of these numbers. We know that 3 of these integers must be consecutive. So either PQR is consecutive or QRS is consecutive. So what we do now is find what the 3 consecutive numbers at least must be and at most must be. So how we can do this is So what we do now is to find the least and most values of the 3 consecutive numbers. Without loss of generality, we can just consider S to be the 3rd integer that's left. So what we do now is to find the possible values for the 3 consecutive integers. So how we do that is to set one of the limits. So now what we do is to find the minimum and maximum values of the 3 consecutive integers. So how we do that is to take the whole sum minus 180 So now what we have to do is find the minimum and maximum values of the 3 consecutive integers. To find the minimum value, we set the odd integer out as the largest possible value, which is 180. So then we see that the sum of the 3 consecutive integers, x, plus the odd integer out, 180, has to equal 527. Using basic arithmetic, we find that x equals 347. Since 347 isn't divisible by 3, we need to find the number right above 347 which is divisible by 3, and that happens to be 348. Since 347 is not divisible by 3, we need to find the number right above 347 which is divisible by 3, and that number happens to be 348. Dividing by 3, we see that we get the number 116. That means the middle number has to be 116. So the number right below has to be 115, and the number right above has to be 117. These are the minimum values for the 3 consecutive integers. Next, we want to find the maximum value. What we do now is to set the odd integer out as the least value, 101. So we get x plus 101 equals 527. So then we solve for x. We see, using our calculator, that x equals 426. Again, we want to divide by 3, and then we see that x equals, and we see that the original next we want to find the maximum values of the 3 consecutive integers. What we do now is set the odd integer out as the smallest possible value, which is 101. So you get x plus 101 equals 527. What we can do now is to solve for x, and using our calculator, we see that x equals 426. Now we can divide by 3 to get the middle integer, and we see that the middle integer is 142. This means that the integer before is 141, the integer after is 143. These are the maximum values of the 3 consecutive integers. So now what we can do is actually try to write out a few of these integers. So the first set, 115, 116, 117, 179. To create a new set, we can add 1 to here. But we have to subtract 3 in order to keep the sum the same. So we can keep doing this, but eventually we'll hit this set. This obviously won't work because PQRS have to be distinct as given by the original problem. So this also marks a turning point where this number starts to become less than the consecutive integers. So we can start writing a new set where this number actually starts at the front. So the next set would actually be and then we can keep writing this until we reach the last set, in which the first number is 101, then we get 142, 142, we get 141, 142, and 143. So this is our final set. So we want to count the number of sets here, and the number of sets here, where this is the set right in front of this set. So after counting, we see that there's 16 sets here and 10 sets here. We can do this simply just by subtracting this from here, which we get 9, and since there's the first set, we know that there's 10 here, and we can do the same thing over here. So next, we want to count the duplicates of the values of s, since we're assuming s is the last number right over here. So then we can just write out all the values of s. In the first set of 16, we get the first value of s is 179, and then we get 176, we're only interested in the values of s, which happens to be the last numbers. So we want to check for duplicates, and how we would do that is to just actually write out every single value of s and check for duplicates. So you start at 179 and then start working backwards. And now we're switching over to the second set. We start at 1, 3, 4, and then move up by 1, since now s is part of the consecutive integers. Now just by inspection, we can see that this and this are duplicates, so we can cross out this one, and then we can cross out this one since it's a duplicate with this. 140 is also a duplicate with this, and then 143 is a duplicate with this. So we see that we subtract 4 duplicates. And since we know that there are originally 26 values of s and there's 4 duplicates, we can see that there are 22 distinct values of s, which is our final answer. The next question we're going to be working on is question 20 from the 2021 Cayley exam. We're given a 4-digit positive integer is divisible by both 12 and 20, but is not divisible by 16. We're asked how many such positive integers are there? So let's call this integer n. And since we know that it's a 4-digit positive integer, we can set the limits from 1000 is less than or equal to n, and n is less than or equal to 9,999. So the next thing we do is to take the least common multiple of 12 and 20. This gives us 60. And this 60 is important because any number that is divisible by both 12 and 20 must also be divisible by 60. And the final restriction is that n is not divisible by 16, which you can write like this. 16 is not a divisor of n. So from here, what we can conclude is that if we have a constant k times 60 is equal to n, where k is an integer. This is how we basically write this in algebra. Then what we can do is to actually find the limits of k, the lower and upper bound. So to find the lower bound of k, what we can do is take 1000, which is the lower bound of n, and divide it by 60. Then we take the least integer that's above that, and we get that the lowest value of k is 17. Now we want to find the highest value of k. So then we do that by finding 9,999 divided by 60, and we find the greatest integer that's less than that. And then we eventually work that out to be 166. So these are the integer values of k, from 16 to 166. However, we need to consider this. This gives us that 16 cannot divide n. And since we know that 60 must divide n, that means k cannot be a multiple of 4. So 4 cannot divide k. So we need to remove all the multiples of 4 from here. We can do that very easily by considering that 20 is right above 4, and 164 is the greatest multiple of 4 that's less than 166. What we can do then is to see that 20 plus 36 times 4 equals 164. So you can conclude that there's 37 multiples of 4 between 17 and 166. Since there are 150 integers between 17 and 166 inclusive, and 37 multiples of 4, we can just take 150 minus 37, which gives us 133 possible values of k. And since n is defined in terms of k, this also gives us 113 values of n, which is our solution. For our final CMC question, we're considering question 24 from the Fermat exam of 2021. So we're given a pair of real numbers, a, b, such that a squared plus b squared is less than or equal to 1 over 4. And a and b are chosen at random. Let p be the probability that the curves with the equations y equals ax squared plus 2bx minus a and y equals x squared intersect. What is the integer closest to 100p? So the first thing we want to do when we're given two curves intersecting is to actually solve these equations. And since both of them are equal to y, we can just write that x squared equals ax squared plus 2bx minus a. So we can move a to the other side, giving us 0 equals a minus 1 x squared plus 2bx minus a. So from here, we should instantly see that this is a quadratic equation. And we can actually solve for x by getting x equals negative b, which is in this case is negative 2b, plus minus square root of b squared, or 4b, minus 4ac. So we get 4 times a minus 1 times negative a, which gives us our 4ac. And at the denominator, we get 2a, which is 2a minus 2. So we want to find out if this equation has a solution. And we know that by looking at the determinant, which is the inside of the square root. In actuality, so in order for x to have a solution, this inside has to be greater than or equal to 0. Or else, if this is less than 0, then the square root function cannot exist. So we basically set an inequality. For b, we can simplify this to plus 4a squared minus a is greater than or equal to 0. So next what we can do is actually expand this out. 4a squared minus 4a plus 4b, there should be squared here, is greater than or equal to 0. So then what we can do is to take out the factor 4, we get a squared minus a plus b squared is greater than or equal to 0. Then we can do a neat trick called completing the square, which means we actually write this as a square. So then we take a squared minus a plus 1 over 4 plus b squared is greater than or equal to 1 over 4. So the neat trick is to actually factor this. We get a minus 1/2 squared plus b squared is greater than 1 over 4. If you don't trust me, you can actually expand this out and you will see that you would get a squared minus a plus 1 over 4. So this should actually be pretty familiar. This and this are both equations for circles. Well, not exactly, since there's an inequality sign, but I'll show you how to deal with that later. So in order to write this as a circle, this is actually the radius squared, and this gives you the coordinates of the center. So if this is our coordinates, we get that a, if we had labeled this as our a and this is our b, a minus 1/2 will actually give us the center of circles here, where this distance is 1/2. And the radius, because the radius is the square root of 1 over 4, that means the radius is 1/2 as well. So we see the circle looks like that. And since there's a greater than or equal to symbol, the possible values of a and b actually live out here, and the inside of the circle is blank. However, we have to overlay this with the actual possible values of a squared, the actual possible values of a and b. So this actually looks like this, where the square root of this is the radius, and then the possible values of a and b live inside of the circle. So what we actually want is the intersection between these two possible values. So if we were to overlay these two graphs, we see that the possible values of a and b are here, and the possible values of the solutions to this equation are over here. And since we want the outside of this circle and the inside of this circle, the possible values live over here. To find that, what we can basically do is take the area of this circle, which is pi over 4, and then subtract this area inside. So the area inside is actually very easy to solve. We can draw a triangle here. This is an equilateral triangle, and since we know the radius is 1/2, we can find the area of this triangle. The area of this triangle is simply square root of 3 over 4 times one of the side lengths, which is the radius, 1 over 4, giving us square root of 3 over 16 as the area of the triangle. However, this entire area over here, this sector of the circle, is just 1/3 of the entire circle's area. And since the circle's area is pi over 4, the sector's area is pi over 4 over 3, which is the same as pi over 12. So the area of one of these halves is equal to pi over 12 minus the area of the triangle, which is square root of 3 over 16. And since there's two of these little sections, we multiply the entire thing by 2. This is a very standard trick for geometry problems involving circles. But we're not actually looking for this area. What we're actually looking for is the area outside of that little sector. So then what we can just do is take the area of the entire circle and minus this. And what we get, pi over 12 plus square root of 3 over 8. However, we're not actually looking for the area of the sector. We're looking for the probability. So then what we can do is have this as a classic case of geometric probability and divide it by the entire space of the possible values of a and b, which is equal to pi over 4. So all we do is take pi over 12 plus square root of 3 over 8 and divide by pi over 4. Simplifying this, we will get 1 over 3 plus square root of 3 over 2 pi, and that's equal to p. But we're not after p. We're after the integer that's closest to 100p, and plugging into our calculator, we get that 100p is around 60.9, which is around 61, which is our final answer. So here's the last question. This question is actually not part of the CEMC exam, but it's actually just a fun question I found myself. So we're given that z is part of the complex set, or z is a complex number, and z plus 1 over z is equal to 2 cosine 3, and 3 is in degrees, not radians. We're asked to find the least integer greater than z to the 2000 plus 1 over z to the 2000. So to approach this problem, we should actually use Euler's formula, which basically states if we have z equals r e to the I theta, we can write this in r times cosine theta plus I sine theta. So now we can plug z into here. So what we get is r e to the I theta plus 1 over r e to the negative I theta. And then we can use this form to write out here. So you get r cosine theta plus I sine theta plus 1 over r cosine theta minus I sine theta. Since from here we have a minus theta, and we know that sine of minus theta is the same as negative sine of theta. So from here we can do some combining to combine the cosine terms. We get r plus 1 over r cosine theta plus r minus 1 over r I sine theta. So from here, since we know that 2 cosine 3 is completely a real number, that means that this, which is still equal to z plus 1 over z, this imaginary part has to go to 0, which either means that r minus 1 over r equals 0, or that theta equals 0. Since we know that sine theta, the sine 0 is equal to 0. Now, if we assume that theta equals 0, then this part cancels out. And then we're just left with this part. And since cosine 0 equals 1, this part also cancels out. So we get r plus 1 over r equals 2 cosine 3 degrees. And since we actually know that this is a quadratic, we can multiply by r on both sides, right? We get r squared plus 1 equals 2 cosine 3 degrees times r. We can find the discriminant, which works out to be 2 cosine 3 degrees squared minus 4. And we can see that this actually works out to be less than 0. So this has no real solutions, and by definition of Euler's formula, r must be a real number, so we see a contradiction. Thus, this completely doesn't work, and we're left that r minus 1 over r must be 0. So solving for this, we see r has to be 1, so then theta must work out to be 3. As a sanity check, we can plug 1 back into here, and then we see that 1 plus 1 over r is equal to 2, and cosine, and then if theta equals 3, we get cosine of 3 degrees, and this is the same as our original 2 cosine 3 degrees. So what we do next is actually use the Moivre's theorem to plug into here. So we see that z to the 2000 plus 1 over z to the 2000 can actually be expanded into cosine we can see that these cancel out, and then we know that theta is equal to 3, so then this finally equals 2 . And then we can simplify this further, and we see that this is 2 cosine 240 degrees, which is equal to -1. And the least integer that is greater than this is 0, which is our final answer.